Hello folks, this video goes through your Chapter 6 study guide, so feel free to skip around to the questions that you need to hear explanations for. So starting at the top, number 1 says change negative 330 degrees to radians in terms of pi. So if I have negative 330 degrees, to get that into radians, I'm going to multiply it by pi over 180. In terms of pi means I want to go ahead and keep this as a fraction. So we're going to multiply straight across. Remember, if negative 330 is technically over 1, when we multiply straight across, we get negative 330 pi over 180. And then you need to simplify negative 330 over 180, which simplifies to be negative 11 pi over 6. Now, there is no unit for radians. I mean, if you want to put like RAD behind it, you can, but it's kind of understood, especially by the directions, that your answer is in radians. Number 2, this says change 60 degrees to radians, rounded to the nearest whole number. So same kind of question, right? I'm going from degrees to radians. The only difference is the way my answer is going to look. So if I have 60 degrees, I'm still multiplying it by pi over 180. So then when I get 60 pi over 180, if I go ahead and reduce that, I get pi over 30. And then to the nearest whole number, over 3 rather. If I round that to the nearest whole number, some people are kind of stuck, like, well, what does that mean, pi over 3? Well, that means literally type pi over 3 into your calculator and round it to the nearest whole number. If you do that, you're going to get about 1. Again, that's a radian, 1 radian. Number 3, change 18 radians to the nearest degree. So now I'm going backwards. I'm going to use this as a reminder to let you know that radians don't always have to have pi in it. Okay, so again, this one just says 18 radians. So now we will do the reciprocal. We're going to multiply 18 by 180 over pi. Okay, to the nearest degree means I can just type this in my calculator, round it. You should get 1031. Make sure if your answer is in degrees, you put the degree symbol. Same type of question, except I've got 5 pi over 12, and these radians to degrees, it does have pi. So when I multiply this by 180 over pi, what happens here is if I do 5 times 180, I get 900, and then I've got pi, and then I've got 12 pi, and then pi over pi is 1, and then 900 divided by 12 is equal to 75. So there's no rounding necessary in this one, just 75 degrees. Moving on, number 5. A sector has a central angle of 135 degrees and an arc length, that word is important, of 114 millimeters. Determine the radius of the circle and the area of the sector created by the angle. Round each to the nearest tenth. So this is a two-part question. So arc length, you need to be able to recall that the arc length formula is S equals R times theta. Okay. The other thing you have to make sure that you remember is that theta in any of our formulas that we're dealing with has to be in radians. Okay, theta has to be in radians. So if they give us the angle in degrees, the first thing we need to do is convert that 135 degrees into radians by multiplying by pi over 180. So if I do that, I get 135 pi over 180. And if I reduce that, then I get 3 pi over 4. Okay, so this is now theta in radians. All right, so now what this means is if I kind of fill in my equation here, S equals R theta, I'm solving, no, they give me an arc length, right, of 114. So that's equal to, I'm looking for the radius, so leave R, and now I know theta is 3 pi over 4. So then if I'm solving to get R alone, I'm going to divide both sides by 3 pi over 4. In your calculator, you must make sure that 3 pi is in parentheses. If it's not in parentheses, your calculator is going to compute 114 divided by 3 pi first and then divided by 4. You need to make sure that that fraction is all together in your calculator. Okay, when we do this, we get our answer for the radius. It says round each to the nearest tenth. So when we do this, our radius will be approximately 48.4 millimeters. Okay, so that's part one. Part two, that's our first answer, says find the area of the sector. So that brings us to our second formula. The second formula for area is equal to 1/2 r squared theta. Well, we have theta and we have the radius, so we just need to substitute in our information. 1/2. Our radius is 48.4 squared times 3 pi over 4. Okay, so then if you plug this in your calculator, you will get that the area is approximately 2,757.8 millimeters squared. Now, if you didn't get that, perhaps you got 2,759.8. That's what happens if you plug this in exactly as you see it here, 48.4. If you, and this is what you should do, leave this value in your calculator with a crazy long decimal, or when you enter in the radius, re-enter in 114 divided by 3 pi over 4, and you will get the closest answer to the real thing without rounding twice. Okay, so that's the deal, is you want to round at the very end only if possible. Number 6. An arc is 18.5 centimeters long. It's intercepted by a central angle of 42. What is the radius of the circle to the nearest tenth? Again, the key here is length. Okay, so if I'm dealing with length, the other thing I noticed is that they give me an angle in degrees, so I want to convert that to radians first. So 42 degrees to radians will be pi over 180, which will be 42 pi over 180. Which will be 7 pi over 30. So this is theta. Okay, 7 pi over 30. So then if I do arc length is equal to the radius times theta, this implies that the arc length, which we know is 18.5, is equal to, again, I'm solving for the radius, so I'm going to leave r, and then we know that theta is 7 pi over 30. So this one is extremely similar to the last question. If I want to isolate r, I'm going to divide both sides by 7 pi over 30, ensuring in my calculator I put that fraction, 7 pi over 30, in parentheses when I divide it from 18.5, giving us the answer for our radius. To the nearest tenth should be about 25.2 centimeters. Number 7. Two gears are interconnected. The smaller gear has a radius of 2. The larger has a radius of 8. If the smaller gear rotates 330 degrees, determine how many radians the larger gear rotates to the nearest tenth. The trick to this problem is figuring out, out of the formulas that we know in this chapter, which one of them actually applies. So the first thing I know is that this has nothing to do with rate, right? This has nothing to do with radians per second, centimeters per minute, nothing like that. There's nothing to do with time. So therefore, I know this is not dealing with angular velocity or linear velocity, okay? It's probably still have to do with area of a sector or arc length. And in fact, if you kind of draw a picture, so gears, are these, it's not going to look pretty, but, it's got these things out like this. So there'll be my small one. The bigger circle interconnected, it's got this gear, okay? And, okay, so they're both circles like this. It says the smaller one has a radius of 2. The large one has a radius of 8. Okay, it says the smaller gear rotates 330 degrees. Determine how many radians the larger gear rotates. So many people say, hey, can I just use a proportion? And the answer is no, because they're not spinning in proportion, if that makes sense. So what you have to realize is, what I kind of imagined was, if my gears were like sitting on a table, or sitting on an ink pad, if I spun this gear, the little gear, 330 degrees, which maybe let's go ahead and change that to radians, since we know we're going to have to anyway, right? 330 degrees into radians will be pi over 180, and 330 pi over 180 is equal to 11 pi over 6. Okay, so this one is spinning at 11 pi over 6 radians. As it spins, if it were on an ink pad, that ink would cover however amount of the gear, right? Well, if this other gear, this bigger gear, is sitting on the same ink pad, as it spins, it's spinning the same amount of time as the other one is, right? For it to get to 330 degrees, that it should also have the same amount of ink on it. So in other words, that allows me to conclude that I need to deal with the arc length formula. Okay, so this means that their arc lengths are similar. Not similar, sorry. The arc lengths are equal is a better word. So if the arc lengths are equal, let's go ahead and do the small gear first. I know if I have S equals R times theta, we don't know what the arc length is. We just know that they have to be the same. So it's going to be S equals, the small radius is 2, and we know that theta is 11 pi over 6, which means the small arc length is 22 pi over 6. Okay, I wouldn't get that as a decimal just yet because I'm going to use this arc length for the larger gear. Okay, the larger gear again, I'm dealing with S equals R times theta. I know that if the arc lengths are equal, then I can substitute this value for S into arc length, 22 pi over 6. I know that its radius is 8, and theta is what I'm solving for. The question is, how many radians does the larger gear rotate? So once I get to this point, I can go ahead and divide by 8 to isolate theta. And when we do that, it says round to the nearest tenth. You should get that theta is approximately 1.4. And again, if you want to put RAD for radians, you can do that. So it rotates 1.4 radians. Number 8, determine the angular displacement of 12.9, I should say revolutions, not evolutions, in degrees to the nearest tenth. So angular displacement is just when think about a wheel spinning, how many, or what angle does it cover? In this case, how many degrees does it cover? Well, if one revolution is equal to 360 degrees, then that implies that 12.9 revolutions, if we multiply it by 360 degrees, will equal a total of 4,644 degrees, okay, because it says degrees. Number 9 is a similar question. It says it asks for the angular displacement of 3.6 revolutions in radians to the nearest tenth. Okay, so again, I know that one revolution of a circle in radians is 2 pi, which means 3.6 revolutions with 2 pi for every one revolution to the nearest tenth should be about 22.6 radians. Number 10, what is the angular velocity of 700 revolutions in radians in 15 minutes? You need to be able to generate the formula for angular velocity on your test. For that, we use omega is equal to theta over t, where theta doesn't just stand for the angle. Well, I mean, it does. It stands particularly for the angular, let me spell this correctly. How about this? Let me just put an angle symbol. So theta represents our angular displacement. Okay, so what that means is when it says what is the angular velocity, I know I'm solving for omega, but 700 revolutions, you don't plug in 700 to the equation because there's no spot for revolutions. We know time is 15, right? But 700 is going to be used to find the angular displacement. So if we go off to the side and do that first, angular displacement, just like we did number 8, number 9, we're going to take, and I didn't say how to round this, by the way, but we're going to round this to the nearest tenth if necessary. So our angular displacement is going to be 700 times 2 pi, which to the nearest tenth will be about 4,398.2. So that's how many radians the circle covers in 700 revolutions. So that's what goes in for theta. 4,398.2 divided by, so this is radians, divided by 15 minutes gives us omega as approximately 293.2. Be careful of your units on this test. I've got velocity, so this is a rate. If you actually write the units in your problem, it'll help you. Radians per minute. Radians per minute. Angular velocity means that would have something to do with an angle. Okay, number 11, very similar problem. What is angular velocity? I got 3.2 revolutions in 7 seconds. We're using the same formula, omega equals theta over t. Again, if necessary, round to the nearest tenth. Step 1, find the angular displacement. To do that, we're going to take our 3.2 revolutions, multiply it times 2 pi, which is approximately 20.1. So there's our angular displacement. Then I get omega is equal to, we're going to take that value for theta, right? That's what theta is. So that'll be 20.1 divided by time is 7. So again, this is in radians. And I got 7 seconds. And 20.1 divided by 7 gives us omega of approximately 2.9 radians per second. Number 12, determine the linear velocity, so there's our keywords, of a point rotating at 27.4 radians per second at a distance of 4 feet from the center of the rotating object. So the first thing to recall is that linear velocity has, I'm going to say it doesn't have two formulas. You could see the formula is written in two different ways. Radius times theta over t, or we know that theta over t is omega, right, from our angular velocity problem up at the top. So it's going to be r times omega. All right, when it says, so look what I got here. I got 27.4 radians per second. That is omega. That's the rate. And then when it says a distance of 4 feet from the center, that's the radius. So this is actually a very simple problem. If I use the second equation, I get v equals, radius is 4, times 27.4 radians per second, giving me a velocity. Again, I didn't tell you how to round, I apologize. Let's do to the nearest tenth. 109.6. I'm in velocity. So this is 4 feet, and this is radians per second. So, right, is it second or minute? Yeah, radians per second. So linear velocity means I'm going to have feet per second. 109.6 feet per second. Number 13, determine, again, the linear velocity of a point rotating at 64.5 pi radians per minute. Distance of 88.9 millimeters from the center, again, that is radius. So very similar problem, omega equals v, velocity equals radius times omega. V equals r times omega. So that's going to be 88.9 for the radius, 64.5 pi for the angular velocity, or omega. Again, to the nearest tenth would be about 18,014. Again, we're dealing with millimeters for the radius, and then we're dealing with minutes for the time. So millimeters per minute is how you find the linear velocity.